Alright, now we move on to the good stuff. We're using L'Hopital's rule now on exponent indeterminate forms. There were three of them, remember. The three of them are 0 to the 0 power, 1 to the infinite power, and infinity to the 0 power. These are the three exponent indeterminate forms. The way that we're going to do these, I'm going to sort of give you a brief overview of the thing. Let's say that you have a limit that's approaching one of these things, right? So I interpret that to mean that you have something like the, something like you have the limit as x approaches a of f of x to the g of x power. What you're going to do is you're going to say this is equal to L. You're going to say, look, I trust the limit exists. Let's just get this done, right? Now that the limit is L, what we do is we take the natural log of both sides. We say natural log L is equal to the limit as x approaches a of the natural log of f of x to the g of x power, right? What that does is it lets us bring the g of x down, right? So you took your initial limit, you set it equal to L, you took the natural log, and that allowed you to bring the power down. Now that you've done that, now that we've brought that power down, and I don't know if you guys recognize this, it'll be a lot more clear in our examples, you now have g of x times the natural log of f of x. And what you've done here, again, I don't know that you guys recognize it, but what you've done is you've taken an exponent problem and turned it into a multiplication problem. And what happens, and this is really neat, if this was infinity to the 0 power, now it's 0 times infinity. If this was 1 to the infinity, now it's infinity times 0, because the natural log of 1 is 0. If it's 0 to the 0 power, now it's 0 times infinity. We've taken one of these exponential forms and turned it into a multiplication one, right? Now that it's a multiplication one, we do what we learned in the last video. We take one of these guys, generally this one, and we write it as a reciprocal. We write this as the natural log of f of x over 1 over g of x. And after a few steps of work, we've managed to get the problem into a fractional form where we can use L'Hopital's rule. The last thing you have to remember is that this is actually equal to the natural log of L, so you have to do that exponentiation trick where you use the big E on both sides. This is the overview of what we're about to do. We'll go into specifics in the examples we're about to do. So here's the first one. The limit is x approaches 0 from the right of x to the x squared power. Right? If we attempt to evaluate for 0, we get 0 to the 0 power, which we know is indeterminate. So I mentioned in the previous slide, what we do is we say, okay, L is equal to this limit. The limit is x approaches 0 from the right of x to the x squared power. Right? But now that we've done that, we might as well just go straight to our next step. We take the natural log of both sides. Right? When I do that, I get the natural log of L is equal to the limit as x approaches 0 from the right of x squared times the natural log of x. And it's actually really neat to see here. What happens if you attempt to evaluate for 0? What happens if you attempt to plug in 0 here? We get 0 times negative infinity. We have successfully transformed this indeterminate form into this one. And that means we can proceed with the way that we know how to do this, right? It's still ln L. Insert Hawaiian food joke here. And on the other side, I'm going to have natural log x over 1 over x squared, right? Because this x squared here turns into 1 over x squared when we put it in the denominator. And again, it's astonishing but amazing. When we attempt to evaluate for 0, we get negative infinity over infinity. Sure enough, this is in L'Hopital's rule territory now. Right? I have ln L equals the limit as x approaches 0 from the right. I'm now using L'Hopital's rule of 1 over x over, and this is going to be negative 2 over x cubed. And this thing is still like, infinity over negative infinity. And this is that same kind of problem we saw at the end of the previous video. It doesn't make sense to keep doing L'Hopital's rule. What we'll do instead is multiply top and bottom by something convenient. Right? What should I multiply by? I should multiply by x cubed. Right? When I do that, I'll get natural log L equals the limit as x approaches 0 from the right of basically x squared over negative 2. And now what happens when I attempt to evaluate for x being 0? This is approaching 0. Notice that at each step in this process, I sort of checked myself, like, hey, I'm still 0 times negative infinity, I'm still infinity over infinity, I'm still infinity over infinity. I'm always checking, like, what is this limit approaching until I get somewhere, right? Now, super, super, super important, the answer is not 0. The answer to this problem is L, and right now we have found that the natural log of L is 0. So what is L itself? Well, this is where you either put the e on both sides, or where you change forms. You recognize, hey, this is a logarithm expression. I can change this into e to the 0 power equals L, which means L is 1. So the answer to this problem, to this limit, is 1. Okay? So L'Hopital's rule can be used for the power expressions. It's complicated, but it can be done. And in fact, you're expected to do it. This is a big component of the Calc BC exam, as well as the Math HL exam when we're doing the series and differential equations option, which is the paper 3. Here we have another limit for us to do. The limit as x approaches infinity of the xth root of x. So this is like the infinite root of infinity. It may be hard for you to see it this way, but if we rewrite it, think about how you could rewrite this. We should be able to do this as x to the 1 over x power, right? If we try and evaluate for infinity, we're going to get infinity to the 0, which is one of our indeterminate forms. So this problem should be pretty straightforward. I bet this one's actually a little bit easier than the previous one. So pause the video, work through this one, and figure out what this limit's going to be, and then check back in to see if we got the same answer. So we set it equal to L. This gives me the limit as x approaches infinity of x to the 1 over x power. I then take the natural log of both sides, enabling me to bring down the 1 over x. So I get ln L equals the limit as x approaches infinity of 1 over x times ln x. Right here, I'll just do a quick check. If I try to evaluate for infinity, I get 0 times negative infinity. Surprise, surprise, it's still indeterminate. I'm still going to keep working on this. This is ln L equals the limit as x approaches infinity. So how could I take that expression right as a fraction? Really easy. We just write ln x over x. As x approaches infinity, this is infinity over infinity. I can use L'Hopital's rule on that, right? So this one gets me ln L equals the limit as x approaches infinity of 1 over x over negative 1 over x squared. This is still approaching infinity over infinity, but we've seen this a couple times now. We just multiply both by x squared. This will give me ln L equals the limit as x approaches infinity of x, basically negative x, right? And so this limit is approaching 0, right? So this means that I have the natural log of L equals 0, just like we did in the last one. L is equal to e to the 0, which means it's 1. So we figured out what this one is. You're going to notice in these problems, like the steps that you do to take the limit as you're going along are a little bit different. Like the arithmetic we did throughout this thing was a little bit different, but the process of setting it equal to natural log, bringing the power down, changing that into a fraction underneath, doing L'Hopital's rule and getting the answer, that is going to stay consistent through all of these exponent-style indeterminate forms. So here's another example for you. This is actually my favorite example. This is a really, really, really good one because the answer is super duper exciting. If you haven't seen this before, be ready to be excited. If you have seen it before, then be excited again because it's still good. If you're up for it, try this one on your own, but I'd recommend checking in from time to time because the arithmetic on this one is a little bit more complicated. In the interest of time, I'm going to skip over some of the beginning stuff. We attempt to evaluate for infinity. We get 1 to the infinity power. So we set it equal to L. We also do the natural log. So I'll have the natural log is equal to the limit as x approaches infinity of x times the natural log of 1 plus 1 over x. Right? Again, those are the first couple steps. They all look very similar to one another. So next up, we rewrite the right-hand side so that it looks like a fraction. Right? So we get the natural log of 1 plus 1 over x all over 1 over x. Okay. We could check in real quick here, make sure we're still in indeterminate form. As x approaches infinity, we get the natural log of 1, which is negative infinity sorry, natural log of 1, which is 0, my mistake, which is 0 over 0. So we're still indeterminate, we keep going, right? I have the natural log of L equals the limit as x approaches infinity, and now, like I said, this is where things get a little bit messy, right? I need to take the derivative of the top and the bottom. So how do we do the derivative of the natural log of something? It's supposed to be 1 over the thing that was inside, 1 plus 1 over x, times the derivative of that thing, which is going to be negative 1 over x squared, or negative x to the negative 2. Right? In the denominator, I just have the derivative of 1 over x, which is negative 1 over x squared. Here's the important thing. When you take the derivative of what's inside, it's going to be the derivative of 1 is 0 times the derivative of this. This derivative and this derivative are going to be the same. We see from a little distance off that these things are both going to divide out to be 1. Right? I hope that was clear. If it wasn't, like, pause and go back and look at this. This exact problem, problems just like this one, are the main reason that we do this. And you'll see why when we get to the answer. I have the limit as x approaches infinity of 1 over 1 plus 1 over x. As x approaches infinity, this approaches 1, so I have the natural log of my answer is 1, and when I rewrite this thing, I end up getting that L is e to the first power, or e. So this limit, it turns out, is e. There's a good reason for this. If you want to stick around for a minute, it's a nice way to tie together some other knowledge that you guys have. This original limit was the limit as x approaches infinity of 1 plus 1 over x to the x power. We've actually seen things like this before. You may remember from sometime in the past the formula for compounded interest was p times 1 plus r over n to the nt power. Notice that this has an n in the bottom and in the power, and n was the number of compounds per year. So if you're compounding monthly, it's 12. If you're compounding daily, it's 365. The day after that in intermediate algebra, you learned about continually compounding. Which is like, what if we compounded infinitely many times per day? In other words, what if that n was limited towards infinity? Right? You would basically get this thing up here, right? And you learned that formula was p e to the rt. It shouldn't be surprising that this limit gives us e. Right? This limit is basically this one with r and t being 1. Right? So if r and t were 1, and if p was also 1, you'd be left with just e. This formula for PERT basically comes from taking this formula for compounded interest and doing the limit as n approaches infinity. It's good stuff. Hope that made sense. The assignment that we have for this is a lot of really straightforward problems in terms of taking these limits and trying these methods. So I'll see you in class.